Hi guys, in this video I'd like to go through some practice problems on calculating pH of strong acids, strong bases, weak acids, and then a mixture of an acid with its conjugate base, which is generally acquired by adding a base to a weak acid solution. So I'm going to start out first of all with the strong acids. So strong acids dissociate completely. And the reaction HCl, if you add water, that's going to break down completely to H plus and Cl minus. Dissociation is referring to dissociation, the loss of the H plus, and it breaks down completely. And if you were to have 10 HCl's, you would have 10 H's and 10 Cl's. Sometimes people might say, well, if I've got 10 HCl's, aren't I going to get 5 H's and 5 Cl's? But think about it. In HCl, how many H's are there? 1. And how many Cl's? 1. In 10 HCl's, how many H's would there be? 10. And how many Cl's would there be? 10. So when it breaks down, you get 10 H's and 10 Cl's. Now remember, pH is the negative log of the concentration of H+, which means that however much HCl you put in, you're going to get, when it dissociates completely, you're going to get that exact same amount. For example, 10 and 10, you're going to get that exact same amount when it dissociates. And so if we just find the negative, if we want to find the negative log of this, it's going to be the same as the negative log of this. So for strong acids, whatever the concentration is in molar, because pH is always the negative log of the hydrogen ion concentration in molar. So for strong acids, whatever the concentration is in molar, just do the negative log of it, and that gives you the pH. Let's look at Y and break it down. So strong acids break down 100%. Classic examples are HCl, HNO3, and H2SO4, hydrochloric, nitric, and sulfuric acids. In my exams, I'm never going to give you sulfuric acids. The simple reason is that notice that this is H2. So for every one of these, you get 2 H+. And honestly, in biochemistry, I don't want to add that complication. So I would rather just keep it simple, just to know that you get the basic idea, and you get that from these two. The general rule as well is that because these dissociate completely, there's going to be no K value. So if you don't see a K value, you know that you're talking about the strong acid. But it is these two, and these two are the ones I'm going to give. Strong bases also break down 100%, and that's going to come up in the next example. Strong bases typically have got this OH group in them, sodium hydroxide, potassium hydroxide. So you'll see them when they come up. But let's talk about our strong acid. We have our HCl, and it is aqueous, that means it's dissolved in water. That's going to break down to give you H plus and Cl minus. And notice it's an arrow indicating that it 100% breaks down. Not partially. It's not one of those equilibria. It's 100% breaking down. And we call this HA because this is the H with the A, which we consider the kind of the conjugate base, to break it down to give you the H and the A broken down, separate, dissociated. That's just the shorthand reaction we use. Now, what if we had a 100 millimolar solution of HCl? Well, that means that this is 100 millimolar before the reaction happens, and then it's going to become 100 millimolar and 100 millimolar, and this is going to all react, so you're going to have none of it left. So let's make an ice table. Normally you would do ice tables with equilibria, but it doesn't really matter too much because this is kind of like an equilibrium, just it goes to 100%. The K value is just a billion. But so we can still kind of use it. Initial, change, equilibrium, or sometimes I'll just say end because of what we end up with. So the initial is that we start out with 0.1 molar. Remember, I said that we always want to do it in molar in this case. There's a case later when it actually doesn't matter. We'll get to that right at the end when we do the mixtures. But for now, we want to make it sure it's in molar, convert into molar, so that we can express the H plus in molar for the pH calculation. So 100 millimolar, divide by 1000 to convert into molar. And that gives us 0.1 molar to begin with. It hasn't kind of reacted and come together yet. But when it reacts and comes together, it's all going to be gone. And you're going to make that much of the two products. And so what we end up with is this. No HCl, and we have our two products, 0.1 molar of them. And remember the definition of pH. The negative log of the hydrogen ion concentration. And now we have the hydrogen ion concentration. So we just negative log it. 0.1 is the same as 10 to the negative 1. So the pH is 1. So that's easy. And that makes sense, right? Because you would expect on the pH scale, running from 1 to 14, 14 is basic. And that's saying that you have a low concentration of protons. 1 is acidic, and that's saying you have a high concentration of protons. And yes, we have a high concentration of protons from adding an acid, and thus we have a low pH. So when you do these calculations, think about the answer you're getting. If you're working with an acid, you're expecting a low pH. If you're working with a base, you're expecting a high pH. And if you don't get that, or you get a number outside of 1 to 14, you made a mistake. You've got to go back and try and fix it. But that's just the simplest terms how to calculate the pH of a strong acid. On the other hand, when calculating the pH of a strong base, you're going to have a similar reaction. But the thing is that notice here, similar process, you're generating OH, not H+. And so if you found the negative log of it, you wouldn't find the negative log of H+. You'd find the negative log of OH. So you wouldn't find the pH, you'd find the POH. And I want to know what's the pH. So you're going to have to do some finagling. But that's okay, because we know the kW of water. Remember, that's that 1 times 10 to the negative 14, which is the sum total of the concentration of H+ and OH-. It's written here. So we know what that number is. And so because of that, we can, since we know this, and you're going to derive this, you can rearrange to make this the subject, and then you know the pH. And so you could just work out you could just do Kw divided by OH equals H+, and then just negative log it for the pH. But actually, we could even make it even simpler. Because if we negative log Kw, 1 times 10 to the negative 14, well, the answer is 14. And so P, I guess you could say pKw, pH, and pOH is going to be 14 equals pH plus pOH. It's going to be plus instead of multiply because because it's logarithmic. And when you multiply these powers, then it's the same as adding powers. So 10 to the 14 is the same as H plus POH. 10 to the 14 is the same as H plus and OH, which is the same as 14 equals pH plus POH. And we can just rearrange it. 14 minus POH equals pH. So let's take a look at this here. We get some sodium hydroxide, solid, those little pellets. We dissolve them in some liquid water. It's going to dissociate completely because it's a salt. It's a salt-strong base, dissociate completely into the sodium ions and the hydroxide ions floating around in the water. I'm going to skip, and let's say we work with a 100 millimolar solution, just like we did last time, and I'm going to skip the ice table, just go to the end. We know that this is going to react completely, so there's none of it, and you're going to get 0.1 molar of each of the products. Now, if I negative log it, that gives me the POH. If I now get 14 and subtract 1, we get 13. And thus the pH is 13. And that's the answer. Now remember, we got a base, so expecting a high pH. And what do we get? A high pH. So that works. So we've got our strong bases now. So we have our strong acids and our strong bases. Things are a little bit different when it comes to the weak acids, because the weak acids do not dissociate completely. They only dissociate partly. So you can kind of think of it as being, well, with the strong acid, if it's say 10 molar, it's going to give you 10 molar of H plus protons. But with the weak acid, if you was to have 10 molar, because it only dissociates completely, you might end up with, say, 9 molar and 1 molar. And the extent to which it dissociates is given by K. And since we're talking about acids, we call it Ka. And so all you have to actually do is that you just have to factor in the Ka. You just take the concentration, multiply it by the Ka, and that gives you it's going to give you the sum total of the two ionic products. So we're going to have to do a little bit of working, but that's essentially it. It's just like the strong acids. It's just that it's not 100%, it's only dissociates maybe 10%. And so you just decrease the product by 10%. That's all there is to it. So if we now go back, now let's start with this question. What is the final pH of a solution when 0.1 moles of acetic acid, that's a weak acid, is added to a final volume of 1 litre? The Ka is 1.74 times 10 to the negative 5. So you know it's not strong acid because it's got a K value, and this K value is to the negative 5, so that's smaller than 1, so that's saying that it favours reactants over products. You're going to have some products, but not too much. So it's not going to have, you're not going to have too much H+, so it's a weak acid. That makes sense. And it's a weak acid, so we're expecting a pH that's going to be, I guess, a little bit higher than a strong acid. The other thing you'll notice is that I haven't given it in molar. I've given it in moles in a litre. And all I've done here is that I've just been tricky, because moles in a per litre is exactly the same as molar. That is the definition of molar, is moles per litre. So moles per litre equals molar. And it's always, remember, when we do our pH, it's always from the concentration of hydrogen ions in molar, which is moles per litre. I'm just being tricky here, so to make sure that you understand your chemistry, the chemistry basis and the definitions. Let's work through the worked problem. So we know the formula K equals products over reactants. And in this case, there are two products, and we are working with an acid. So Ka equals, if this is Ha, this is A minus, and this is H plus. Ka equals A minus H plus over Ha. So our acetate ion and protons over our acetic acid. Now, if we were to just substitute in a few things, we want to know the value of H plus. So we're going to try and solve for H plus. I gave you guys the Ka already. I gave you guys the Ha already, and we want to solve for X because X is H plus. Now, what we can do first of all is rearrange. And we make it so that now we've just got Ka multiplied by Ka multiplied by Ha equals the sum total of the products. And we know that the products are going to just be X. We don't know what they are yet, but we know that whatever they are, it's the same number. Because remember, you get 10 of this, you get 10 of this, and 10 of this. Or you're gonna, with the strong acid, you're going to get, you would get 10 of this and 10 of this and 10 of this. But for every one molecule of this, there is one A minus and one H plus. So you know that whatever you get, if you get one of this, you get one of this. You get X of this, you're going to get X of this. So we know that they're the same number, and so X multiplied by X is X squared. So the sum total of the products is X squared. Now we don't want the sum total of the products, we only want one of them, but we'll stick with this for now. First, now we're going to multiply this out. This is the value of X squared. How do we go from X squared to square? We square root it, and then this gives us the value of X. which is the value of each individual product. And that includes our product of H. And now we know the concentration of H+. And now we can just go up and get the negative log of it to get the pH. So let's run through that real fast. First of all, you want to substitute in the numbers, rearrange, multiply out, square root, which gives you the value of H+, and now the pH is the negative log of the H+, which in this case is pH 2.88, and that's acidic. So yes, we are expecting the solution to be acidic, and this is an acidic pH, but it's not as acidic as our strong acid solution, remember? So that makes sense. The strong acid was a pH 1, and so this is not as acidic as a pH 1. So yeah, that makes sense. So we can say that yeah, the answer is probably correct. Now, when it comes to the mixtures, these mixtures are going to be behaving as buffers. I'm going to give you a little bit of background before I move on to the math. So with the mixtures, what's important to know is that the mixture is going to create buffers, and you're going to have a mixture of HA and A-. Now, because of understanding Le Chatelier's principle, that's saying that if we were to introduce another acid, a second acid, what's going to happen is that you're going to increase the concentration of H+, thus increase the concentration of products. Thus, Le Chatelier's principle, this equilibrium, is going to shift over, and some of the A- and H+, some of the products are going to react and do the backwards reverse reaction to make some more reactant. So if a stronger acid adds in more H+, you're going to force some of the weak acid's product to recombine and do the reverse reaction of making more reactant. And so what is happening is that this acid is becoming protonated and moving backwards. It becomes protonated by the stronger acid. On the other hand, if we were to remove some acid instead by adding a base and doing the reaction of base, which is OH- plus H+, to give you H2O, what you've done there is that you've removed some H+, some protons, thus increasing the pH, because remember, increase in pH is when you remove protons, it's a lower concentration of protons. So if I add some base, I remove some protons, thus I have less product, and so I'm going to get the forward reaction. It's going to move to the right to make up for that, to get back into equilibrium. And it's going to be the same actually when you have a weak base on the other side. If we have a weak base and I add some protons, it's going to make the reactants heavier, and so it's going to move across to the right to make more products to balance out. Or if on the other hand I was to remove some protons, it's not going to move over to the right. In fact, instead, if I was to remove protons, increase the pH by adding a stronger base, if I remove some protons, then that means that I haven't got as many protons. And so this is going to, the product is going to break down back to reactants in order to lose a proton and restore the protons over here. And that's the basis of buffers. A buffer is kind of like a sponge. It's when you it's a weak acid or a weak base, that when you add something, when you add a stronger acid or stronger base that is changing the pool, the total pool of hydrogen ions, the weak acid or weak base is going to release or take up some protons in order to compensate for the protons that were lost or gained by the addition of the stronger acid or base. That's what a buffer is doing, and thus maintaining the normal level of protons. Now, this is dictated by the Ka, right? Because the Ka is telling you how much it's over one side or the other, and thus it's going to tell you how much the equilibrium is going to seek to get things back if you disturb that equilibrium. It's telling you about how much change it can resist and how it's going to adjust to fix that change. And in order to put, if we have pH on this side, then we need to have pKa in the middle here. It just makes it so that we can compare them. It just means that if we increase this by 1, 2, 3, we're increasing this by, this is going to take note in factors of 1, 2, 3. Whereas if it was H plus, it would be by 10 to the 2, 10 to the 1, 10 to the 2, 10 to the 3. And so this is going to be 10 to the 1, 10 to the 2, 10 to the 3, whatever. We always express it as pH. So we're always going to express this as pKa, which makes it easier to work with. The rule is when pH is greater than pKa, then the species is going to be deprotonated. When the pH is less than pKa, the species is going to be protonated. And that works both ways. When pH is greater than pKa, then it's going to be deprotonated. When pH is greater than pKa, it's going to shift it over here and be deprotonated. For the weak acids or for the weak bases, if pH is greater than pKa, what you're saying is that you haven't got enough protons, and so it's going to move over to this side and thus be deprotonated. On the other hand, when pH is greater than pKa, what you're saying, when pH is less than pKa, you're saying that you have a lot of protons, and so you, in the weak acid, you're going to move over this way, and so there is, you have a lot of protons. I apologize. When pH is less than pKa, it's saying you have a lot of protons, and so you're going to be moving over to the left, and so it's going to be more protonated. Or you're saying that on this side you have a lot of, for the weak base, you have a lot of protons. This side gets heavy, so you're going to move over this side to get protonated. So it works in both ways. If in basic media, you're going to move the acid over to here and the base over to here, which is representing deprotonated. With acidic media, what you're saying is that you're moving the acid over to here or the base over to here to be protonated, because you're putting pressure on the opposite side. And when the pH is equal to pKa, that's when you're saying you've actually got a 50-50 mixture of HA and A minus. And on a scale, that looks like this. If we take this acetic acid with pKa of 4.76, well, 4.76 pH is right here. Ooh, that's more like 5, but you get the idea on the pH scale. And so what you're saying is that when the pH is greater than pKa, it's deprotonated, and when it's less than pKa, it's protonated. Because when pH is greater than pKa, you're saying you don't have that many protons, so it's going to lose a proton to make up for it and become deprotonated. And when you have a pH of less than pKa, you're saying you have lots of protons, and so you're forcing it to take one up instead, because the product is heavy, so you're going to move across the reactants. And we can actually look at this if we were to titrate it. If we look at a acetic acid solution, and the pH of that acetic acid solution on the y-axis, as you add more base slowly to that solution, at the beginning where you got no base added, the pH is low, as you expect. And it is going to be mostly in the protonated form because it's a weak acid and it doesn't get very protonated. Remember, the K value is less than 1. So it's going to be mostly in the protonated form. But as we add more base, we're eating up some of the H plus in solution. We are slowly increasing the pH. And so what happens is that at first, the acid starts to give away its proton to make up for the proton that's being eaten up by the base in the reaction making water. But what's going to happen is this is going to happen quite rapidly at first, but when the pKa, remember that's 4.76, when the pH rises to the point where it gets to about pKa plus a minus 1 of that, the weak acid is going to start buffering, and it's going to start compensating for the change that is occurring because of the OH, because of the addition of base. And so at first it's not doing very much, but later the flat part of this sigmoidal curve, what is happening is that as the OH is eating up protons, thus increasing the pH, After a while, the weak acid starts to compensate for it and releases protons to compensate for it, so the overall pH isn't affected as much. And that is going to be plus or minus 1 of the pKa. Remember, when the pKa is equal to the pH, that is when you have a 50-50 mixture of HA and A-. And then as we continue adding base, what's happening is that now a greater than 50% of the weak acid has given away its proton, and now it's going to be majority in the anion form, so mostly deprotonated, until it gets to the point where it can no longer compensate anymore and the pH starts to rise rapidly again. So in the flat region, we can say that it is buffering, it's controlling the pH, because it is making it so the pH doesn't change as much. And now we're going to get back into the math, and we're going to do the final math problem, because for every graph there is an equation. And so in our buffer solution, we have a mixture of our acid and our conjugate base. And so if we add more strong base, it is going to release protons to compensate for it, becoming AC minus, but at the same time compensating for the H plus that was lost, so there's no overall change in H plus. On the other hand, if we add a strong acid, it's going to combine with some of the AC, some of the anion, the A minus that was present, and combine to become a greater amount of the protonated acid. To add base, it becomes more deprotonated, adds more acid, it becomes more protonated, and that is going to be, the proportion is dictated by the Ka, and since we reflect H as pH, we reflect Ka as pKa. Now, like I said, this can be presented as a graph, and we already know that this here, the HA, breaks down, dissociates to H plus and A minus, and we know that that is dictated by a K value, Ka, and we know that Ka is equal to products over reactants, and here's our products over reactants. Now, like I said, we reflect H plus as pH, so we can P this and P this, and then if we move this over and rearrange everything, so if we move it, move it over, rearrange everything, derivatize it, we get this, which is the Henderson-Hasselbalch equation. The pH of a solution is equal to the pKa of the weak acid plus the log of the concentration of the conjugate base and the concentration of the remaining weak acid. Because some of the weak acid is broken down, so what is the ratio between these? Log it, add it to the pKa, and that is the current pH. And that applies to this graph here. When we add more base, we are changing the ratio of HA to A minus as we add more base, and the pKa stays a constant, and in doing so, the pH is changing. Let's work through a practice problem. First of all, what is the pH of a solution containing a mixture of 100 millimolar acetic acid, that's the HA, and 50 millimolar sodium acetate, that's A minus. The Ka is 1.8 times 10 to the negative 5. Now, first of all, this is the Ka, not the pKa. So what do we do to Ka to turn it into pKa? You negative log it. Now we have everything. We can feed this into here. We can feed the HA, 100 millimolar, into here, and we can feed the A minus, 50 millimolar sodium acetate, into here. And now we can just feed it all in. We know the HA, we know the A minus. We can add in all of those numbers. We're going to solve right to left. So 50 divided by 100 is 0.5. You can log it to give negative 0.301. And then when you add a negative number, that's the same as subtracting, to give you the final pH, which is 4.449, so 4.45. pH equals 4.45. Some people say, hey, wait a minute, I thought we had to express this in molar. How come you're expressing it in millimolar? Because it doesn't matter, because we're doing a ratio. It doesn't matter if it's 50 millimolar divided by 100 millimolar. The answer is 0.5. If it's 50 molar over 100 molar, 50 divided by 100 is still 0.5. If we convert it from 50 millimolar is the same as 0.05 molar, and 100 millimolar is the same as 0.1 molar, well then it's the same thing. 0.05 divided by 0.1 equals 0.5. It's the same thing. So it doesn't matter. You don't. In this case, we don't need to, because the units aren't important. It's just the ratio of A to B that we're at. As long as they're the same units, it doesn't matter. Just find the ratio of A to B. So I'll run through that again. What you do is that first of all, you look at the question, and the questions are going to be phrased like this. You look at the question, you look at the Ka, you find the pKa. You look at where Ha is, you look at where A minus is, you find them. You plug them into the equation. You solve the ratio of the ions first, log it, add them together, and that is the pH. No problem. That's the easier questions I'll give you. There's also some harder ones I'm going to give you as well, where you're going to actually kind of be preparing a buffer. Now, for these ones, I say, well, you have for example, this much of HA, and I'm going to add this much base. Now, base is not A minus. Base makes A minus, but it's not A minus. And so we're going to have to do a little bit of reaction. We're going to have to do some of those chemical reactions, stoichiometry, and we're going to have to first now calculate how much A minus there is by titrating how much is made by the addition of the base to the weak acid. And we can use an ice table. And actually, I'm going to, when this happens, I'll warn you by saying use ice. So first of all, we calculate I've given you the Ka. So first of all, we can calculate the pKa, and we can plug into this at the top. Next, we know that acid plus base makes salt plus water. So we know our acid, we know our base, and we want to solve for salt. And actually, we don't care about water. So we can construct our table. We don't care about the water. We'll put an initial. So this is before anything has reacted. We have 510 millimolar lactic acid, 230 millimolar of KOH, but we haven't produced any of the lactate ion yet. It hasn't, nothing has happened yet. Hasn't reacted yet. This is the beginning before that occurs. But what the change is going to happen? The change is going to happen is that this is going to react until one of the reagents runs out. Which is the reagent that's going to run out first? It's going to be the one with the lowest number. Now, if it was, for instance, 3 acid with 1 base, then you'd have to divide this by 3 in order to kind of figure that out. But that's not the case. Instead, because this is a 1-to-1 reaction, it's just going to react until the lowest one runs out, and then it's just going to stop there. So that means that the lowest one's going to run out, so you're going to lose 230. Because that 230 is reacting with this, you're going to lose 230, but because this is reacting, it's going to produce 230 of this. So the next level of the table looks like this, and that's going to give a grand total of this. And now we have our HA. This is our base, but it's all gone. We have our A minus. And now we can take those numbers. We can plug in the pKa that we calculated a while ago. We can take the HA, the A minus, plug it in, solve just like before, and that will give us the pH. So this type of question, you have to do a pre-equation, because I don't give you A minus, I give you the base. You work out how much A minus you've got by reacting the base with the acid. And then finally, I just wanted to give you an example of one of the times where maybe I'm going to be tricky. But look at this question here. A benzoic acid solution has a concentration of 0.1 molar. The Ka is 6.46 times 10 to the negative 5. Okay, it's not sulfuric acid, it's not hydrochloric acid, it's not nitric acid, and it has a Ka, it's a weak acid. The molecular weight is 122 grams per mole. What's the pH? Now, we don't care about this. I'm just being tricky. And so actually with a lot of this, because you don't care about the molecular mass of this, we've already got the molarity, it doesn't matter. So a lot of this stuff we can ignore. And actually we can just break it down. What the question is saying is, we've got this much of the acid. The Ka is this. What is the pH at half equivalence point? Well, that means that what we're going to do is that it's at half equivalence point. That means however much of this, you got the same amount of this. And we know that it's 0.1, and I've crossed it out. So you may think, well, why have you crossed it out? But you'll use it. We'll come to it in a moment. It's going to be 0.1, that's half equivalence point, so it's going to be 0.1. 0.1 divided by 0.1 is 1. And so it doesn't matter if it's 0.1, 0.2, 0.3, or 10,000. It's going to be the number divided by the number, so it actually doesn't really matter what the number is. It's always going to equal 1. So at half equivalence point, this number and this number are going to be the same, and the overall is going to be 1, because it's the same number divided by the same number. Log of 1 is 0. So what you're saying is pH is equal to pKa plus 0. Well, in that case, it's just pH is equal to pKa. And so remember what I said? At half equivalence point, when you have a 50-50 of HA and A minus, pH is equal to pKa. Or the other way around, when pH is equal to pKa, you have 50-50 of the acid and the anion. And that is the reason why. And that is just a quick run through of some practice problems and a quick run through of the content that you're going to find in my quizzes, my exams, and on the homework. I hope this helps.